And the bees are the people who contributed to this presentation, and the people who are contributing to the developments that I will be reporting today. So here are the bees. And there are many of them, so I won't name any particular person now. I will mention some of them later on in the presentation. They are the original bees, the babies, the new bees, and the honorary bees. As the webinar title indicates, and the content simply comprises two parts. I will first explain the bees algorithm and its various implementations. This is the focus of the presentation.
To use the question function
Then I will briefly review some of the applications of the bees algorithm in electrical and electronic engineering. The bees algorithm is a nature-inspired optimization tool. The algorithm can be used to find the maximum of a fitness function or the minimum of a cost function. Functions can be very complex, and a complex function can have many parameters to adjust, sometimes thousands of parameters. And there are many stationary points, many optima. And the aim is to find the global optimum. So in this case, this is the global optimum, and we want to find that in a very efficient manner. And the bees algorithm enables us to do that. The bees algorithm, as you will see, is based on how bees search for food in nature. We will start by briefly reviewing bees' foraging behavior. I will then explain how the basic bees algorithm works, giving a simple example to illustrate its operation. This description of the bees algorithm will conclude with a summary of the additional features making up various implementations of the algorithm. A honeybee colony can have thousands of bees. About 10% of the colony is sent up to 10 kilometers around the hive in search for food. These are known as scout bees. When they have found an interesting food source, they return to the hive to recruit more bees to follow them and gather food and bring it back. To recruit additional bees, the scouts perform a dance. The other bees in the hive observe the dance and then decide which scout to follow. This video shows what the scout bees do in the hive. And I'm going to try and show you the video.
Honeybees have some fascinating abilities, among them being able to communicate by performing a unique dance. It informs hive mates where a newly discovered food source is located. Every cycle of this waggle dance roughly describes the shape of the figure 8. Let's rewind and look in more detail. The bee only waggles on a part of its route, the straight run, indicated here by the waved line. The secret lies in the direction of the straight run, or to be more precise, in the angle between the straight run and the perpendicular, which in this case is 90 degrees to the left. This tells the other bees that food is available 90 degrees to the left of the sun. If the angle is 60 degrees to the right, they'll be flying at 60 degrees to the right of the sun.
Hopefully you can hear me now.
We can hear you.
Thank you. So the bees use this information, which received from the dance, to decide which scout to follow and which flower patch to visit. According to the quality of the patches can be visited by more or fewer bees, or even abandoned. So here you see two patches. This is a small patch, and it attracts 3 foragers. This patch is more abundant in food, and it attracts more bees, more foragers to come from the hive. There, you have seen the main points of the bees algorithm. The scout bees explore the landscape. They do so randomly. They fly around, they explore the landscape. And then they come back to the hive and they recruit additional bees to help them exploit the discovered food sources. The more abundant the food source, the more foragers will be recruited. When nectar and pollen in a flower patch run short, the bees stop foraging it and move elsewhere. So here is the basic bees algorithm. The scout bees initially move randomly in the field, looking for flower patches. So this is the initialization of the algorithm, with N scout bees distributed randomly in the field. When they have landed in a flower patch, the quality of the patch is evaluated. So this is the evaluation of the scout bees that found high quality patches are allocated follower bees to help them exploit those patches. The scout bees that found the very best quality patches are allocated the highest number of followers. The scout bees without followers are again sent randomly. So they are sent randomly because they have not found a good quality patch. They're sent randomly to search for other patches. And then the cycle continues until a certain criterion is reached to stop the algorithm. So this is how the basic algorithm works. Now I'm going to illustrate how the bees algorithm works using a simple example. But you can see that the bees perform local exploitation as well as global exploration. So this is the global exploration part, and this is the local exploitation part. And you will see that in the example that I will show you now. So here is a very simple function, and the aim is to find the peak of the function. You will not use a bees algorithm for this function because it's very simple. You can use other algorithms to find the true optimum. But the bees algorithm is used here just to illustrate how it works. So in this case, we have 10 scout bees, and you saw the scout bees randomly distributed along the landscape. So along the landscape, you see the 10 scout bees randomly distributed. Then we select the 5 best scout bees. So these are the best ones. These are the best patches. We select them. 5 is a number that we choose. We could choose a different number, but in this example, we choose 5. And amongst those 5, 2 of them are even better than the rest. So I highlight them as blue squares. And the white squares are the other selected patches. So these they are. And we build neighborhoods around them. So these are the neighborhoods of the patches, the neighborhoods. And we will recruit bees to come to these patches to exploit them. And from these patches, we select again the best point, and we start building more neighborhoods around those. So you will see that now. So there are these 5 bees. They go to the blue, and there were 3 bees to the white squares. And then we select the best bees from those patches. So now we have new bees plus the 5 randomly allocated bees for scouting. So these are the orange circles. Then the cycle continues until we find the true optimum, which is here. So this is how the bees algorithm works. It's very simple. It consists of exploitation, exploration, and that continues in cycles until we reach the value that we want. You might ask, what's the difference between the bees algorithm and other algorithms, such as particle swarm optimization or ant colony optimization? I can point out here 3 main differences. One is, with the bees algorithm, there are no complex interaction media for exchanging information. So, for instance, we don't use pheromone. In the basic bees algorithm, there is no pheromone employed. There is also in the bees algorithm a clear distinction between exploration and exploitation. This distinction is later on not used in a new version of the bees algorithm. But in the basic bees algorithm, there are 2 phases, exploitation and exploration, and they are separate. In the bees algorithm, there are also mechanisms built in to help the population remain diverse. And because of that, we can avoid being trapped in local optima, which is a big problem for optimization algorithms. So in the bees algorithm, we use random scouting that you saw earlier, and also site abandonment will enable us to abandon sites that do not improve. So therefore, we don't get trapped in them. There are other exploitation strategies that can be implemented with the bees algorithm. Here are 2 of them. One is the neighborhood shrinking strategy. So you saw in a previous slide, we built a circular neighborhood around a site that is found. Now, we sent the bees, the foragers, to this neighborhood to look for new food. And if we don't find an improvement, if we don't find that the solution improves, then we shrink the neighborhood. We make it smaller and smaller and smaller. So we focus the search. Now, if that doesn't work, after a while, we abandon the site. So if no improvement is achieved after a number of shrinking cycles, we abandon the site. So these are 2 exploitation strategies, and they are built into the basic bees algorithm to give the standard bees algorithm. So in our group, we call the standard bees algorithm, which is the bees algorithm made up of the basic bees plus these 2 strategies, neighborhood shrinking and site abandonment. With the bees algorithm, you can add different kinds of local search operators. And you can have a new version of the bees algorithm by adding a new search operator. For instance, you could add the genetic operators and have a bees algorithm which has genetic operators. Or you can add these fancy operators known as segmentation, local quality, and dynamization, which are inspired by the TRIZ method. And this idea was pursued by Mei Chu Ang and Kok Meng Ng, who were with us in Cardiff many years ago. And then we have other operators like interpolation, extrapolation, and creep. These were operators proposed by our friend, Dr. Tuan Pham. He also was a visiting bee at our lab in Cardiff many years ago. And within a short time, he proposed these very excellent ideas. I will mention another idea in a minute to you, also proposed by Dr. Pham. There was another local operator invented by our excellent bee, Ahmed Hash Darwish. He's now a professor in Syria, and he proposed the Kalman filter. So he has used the Kalman filter as a local operator in the bees algorithm. You can invent more local operators. Depending on the problem, you may find that certain operators work better than others, and you might invent your own, and you are invited to do so. Now, here is a very nice idea proposed by Tuan Pham, and this idea is based on the fact that when we create some new scout bees, they are not as strong as the established bees. And if you allow them to compete with the established bees, they will never win. So what Tuan suggested was that we protected these new bees and enabled them to compete amongst themselves for a number of iterations before we release them in the wild to compete with established bees. And this enables us to explore the landscape and find new peaks that are taller than the existing peaks. And therefore, we can find, we have a better chance of finding the global optimum. There are many versions of the bees algorithm. I cannot go through them all. If you are interested, you are invited to read this review paper by another bee, Shah Saran, and her team. She wrote a very nice paper published a few years ago, and it summarizes the different versions of the bees algorithm and their applications. So you are warmly invited to read that paper to find out more about the bees algorithm versions developed until 2017. There are new versions since then, and they are not covered in this particular review, but you can find them somewhere else. I will indicate that to you a bit later. So with the bees algorithm, you can form new versions by hybridizing the algorithm with other established optimization tools, like the ant colony algorithm. And it was hybridized in order to use the pheromone idea to increase interaction between the bees. And this was pursued by our colleague, Dr. Michael Pakianatha at Cardiff University. And there was another researcher, Sami Otri. He also was working on ant colony optimization, hybridization with the bees algorithm. Particle swarm optimization has also been researched as a possible method of hybridizing with the bees algorithm, and that was looked at by Michael Sholedolu. Here, the elite and other successful scouts can act together as a swarm or as leaders of their own swarms. So that idea, those ideas were investigated by Michael. You can use simulated annealing or direct annealing in combination with the bees algorithm. And this can be used to update all the elite and non-elite bees. And these ideas were investigated by these researchers, by Dr. Yuan and his colleagues, quite recently. The genetic algorithm and differential evolution algorithm have also been hybridized with the bees algorithm. And this idea was most recently investigated by Dr. V and his student, Miss Anne. The Firefly algorithm has been hybridized And other algorithms, crow search algorithm, fuzzy logic has been hybridized also with the Bayes algorithm. And artificial neural networks have been used in combination with the Bayes algorithm, support vector machines, and even deep neural networks have been used in combination with the Bayes algorithm. The possibilities are limitless. If you are interested in the Bayes algorithm and doing research in this area, then there are many, many possibilities. I give my hands up. I put my hands up and I say that the Bayes algorithm has also some problems. One problem is that there are many learning parameters to optimize. So you saw that there was something like 6 parameters in the basic Bayes algorithm and 7 parameters in the standard Bayes algorithm. And the Bayes algorithm for some problems can be slow. It can take a bit of time in order to find the true optimum. So those 2 problems have been addressed by various researchers, including people from our team. I will mention some of the solutions shortly. But the Bayes algorithm has many strengths. And one of the strengths is that it has a very effective search strategy, enabling it to mobilize resources to the more promising areas so that it doesn't waste time in areas that are not so fertile. The Bayes algorithm is very suitable for complex optimization problems involving narrow valleys and holes. So the algorithm can find them and locate quickly or reasonably quickly the deepest points in those landscapes. And then, despite the fact that there are many parameters, these parameters are actually quite simple to tune. So it's not too difficult to use the Bayes algorithm. In fact, it's very simple. If you know how to use it, it's extremely simple. And even with 6 or 7 parameters, the Bayes algorithm has been adopted by many researchers to solve complex optimization problems. But I'm now going to show you something recently developed in our lab by Dr. Asrul Ismail in his PhD research. And he developed a 2-parameter Bayes algorithm. And his 2-parameter Bayes algorithm follows the procedure of the basic Bayes algorithm. So you see initialization, site ranking, recruitment, exploitation, site updating, etc., etc. So it's very similar to the, in fact, it's the same in terms of the steps as the basic Bayes algorithm. There are 2 differences, and they are in the recruitment phase and the exploitation and exploration phase. And as I mentioned, the algorithm only uses 2 parameters. The number of scout bees. So scout bees, you need to specify. In this example that I show here, there are 2 scout bees. There's this big scout and a smaller scout. The big scout is the one that has performed really well. So we give it quite a few followers. We give it 7 followers here. And 7 is the number that we specify here. So this is the number of bees allocated to the best scout. So in this case, the best scout is this one. We allocate 7 bees to it. And 7 is our choice. So that's the only 2 choices that we have to make. One is the number of scouts, 2, and the number of bees allocated to the best scout. The bees allocated to the next scout are computed using a function. So the function is a decreasing function. And in this particular case, the function is to divide by 2. So we have 7, we divide by 2, we get 3. 3, we cannot have 3.5 bees, so we have 3 bees. So these 3 bees follow this scout. So this is the recruitment. So this is how we do recruitment in the new Bayes algorithm. In the exploitation and exploration phase, we do something different as well. And this is, we allow these foragers, these follower bees, some of them to do exploration and others to do exploitation. In the case of the best bee, a lot of the bees will follow the best bee and do exploitation. But one or two bees might stray away and do a bit of exploration on their own. And in the case of this second best bee or the poor bee, then more bees will do exploration than exploitation. The number of bees for exploration and exploitation will be decided or is decided by using a particular function that we build into the algorithm. So you can see here, this best bee comes to the patch and it is followed by 6 of its 7 bees. The 7th bee flies away and does a bit of exploration. In the case of the other bee, then 2 bees do exploration, 2 bees do exploration, and only 1 bee focuses on the exploitation. There is quite a lot of details that you can follow, and if you like, you can read Azru's thesis, or there is a chapter that he has written from his thesis, and you can also read that. So that is to address the problem of the number of parameters of the Bayes algorithm. Instead of having 6 or 7, we now have only 2 or 3. The next algorithm was developed by Dr. Jianjie Song and his colleagues in China. And this is a dual population Bayes algorithm. In this algorithm, there are 2 populations. There is a search population and a supplementary population. In the search population, we have bees that are above the average of the total population. So the total population consists of the search and the supplementary population. So the bees that are in this population, they are above average bees. And the bees that are in this supplementary population are below average bees. The below average bees are kept in the population in order to increase diversity. The search population, bees in this search population can be demoted to the supplementary population if their performance falls below the average. On the other hand, bees from the supplementary population can be added probabilistically to the new population of bees in order, as I said, to increase diversity. Again, you can read more about Dr. Song's algorithm in this reference, which is also the reference where you will find the chapter on the 2-parameter Bayes algorithm. By the way, I need to mention that the version of the Bayes algorithm used by Dr. Song and his colleagues is not at all similar to the standard, to the basic Bayes algorithm that we saw earlier. Yet it's still a Bayes algorithm, and this shows the possibilities that you can have in doing Bayes algorithm research. You can have different kinds of techniques and still work on the Bayes algorithm. The next version of the Bayes algorithm is a super fast Bayes algorithm. And it is developed by our colleague, Dr. Yuanjun Lai Li in China also. And this population, this algorithm uses only 3 bees in the population. It has the best bee, the middle ranking bee, and the poorest performing bee. So there are 3 bees and they are placed in this ranking order. The best bee is used for local search, and this search is a greedy search. The middle ranking bee is used in to conduct an evolutionary type of search. And we apply crossover and mutation to it. And the poorest performing bee can be used, for instance, to combine with the top bee, to combine with this second performing bee to give the next generation of bees, or it can be discarded. In either case, we generate a new scout bee randomly. So we preserve diversity in the population. So this bee is used for preserving diversity. This bee is used for fast convergence, and this bee gives both, can give convergence as well as diversity. You can read more about the algorithm in this paper by Dr. Liley. Now, I'd like to review a couple of applications of the Bees algorithms, simple applications. One is digital filter design, and they are applications in the field of electrical engineering, of course. So here is a two-dimensional recursive filter, and this is the transfer function of the filter. We want to achieve a filter with this amplitude response, which is a flat response in a certain frequency range, dropping down to another flat response, and then dropping down to zero outside the frequency range of the filter. The objective function of this filter is like this. We want to minimize this J because we want to minimize the difference between the real amplitude that we obtain and the desired amplitude. And the optimization problem is written like this. Find this vector X, which comprises these parameters. So it's quite a few parameters here. In order to minimize J, this objective function, subject to these constraints. And these constraints are known as Huang's theorem. And they are there in order to ensure stability of the filter. The results are like this. Here is the desired response. Here is the response that we get from our Bees designed filter. Here's, in comparison, the response obtained using the genetic algorithm, another optimization tool. So you can see that this resembles this more than this. I want to move this panel so that I can return to the main presentation. Okay, so now we have seen a couple of applications. There are other applications of the Bees algorithm which are more generic here. So the Bees algorithm has been used to train artificial neural networks to perform classification tasks in electrical engineering and electronic engineering. They have been used to train even deep neural networks, again, to perform tasks in electronic engineering. Tasks such as optimizing the design of a motor, maximizing the power output of a wind turbine, and so on and so forth. So these are the various applications of the Bees algorithm in electrical and electronic engineering. There are many more. I cannot cover them. You can find applications of the Bees algorithm in these workshops. We have held 2 of these Bees algorithm and its applications workshops so far. The first workshop produced a book focused on applications in production and manufacturing engineering. The second workshop has other applications in engineering. And the third workshop which is coming in November, has applications in different areas of engineering and in electronic engineering and other kinds of engineering too. So, in conclusion, in this presentation, we have described the Bayes algorithm, how it works. We have seen that the Bayes algorithm is based on how bees forage for food in nature. And they do that using scout bees that perform exploration, forager bees that perform exploitation in the case of the basic Bayes algorithm, or they can perform both exploration and exploitation, as in the case of the two-parameter Bayes algorithm. We have seen three versions of the Bayes algorithm to address the problems of multiple parameters or slow convergence. So we now have a super fast Bayes algorithm and a two-parameter Bayes algorithm and the dual population Bayes algorithm developed by our friends in China. We have seen a few applications of the Bayes algorithm, and in fact, there are too many applications. ASRUL found over 500 applications in all disciplines so far. I have a suggestion for people in the audience who attend today's seminar. And they are currently, if they are not currently working on the Bayes algorithm, they are observing. They are observer bees. So here is a suggestion for them. Why not spring into action and become forager bees? There is so much more to explore and exploit. For example, you could consider applying the Bayes algorithm to an optimization problem in your particular domain. The new versions outlined here have only been used for problems in production and manufacturing engineering. You are likely to find them useful for your problems as well. If you have employed other optimization tools, how about comparing your results with those obtained using the BA and then come and present your research at our next international workshop on the Bayes algorithm and its applications. Participation is free, and I know you will be most welcome. Thank you. Thank you, Cécile.
We would like to thank Professor Duc Pham for his presentation. If you have any question, now is a good time to use the question function, and the professor will answer shortly.
Cécile, I have lost my my question panel. Let me see. I need to close. Let me close this this presentation so that I can see the panel.
Okay. And at the moment, there's no question.
Hope the audience has not gone to sleep.
I think you were very clear, so they understood everything. And do you have any question? Oh, well, actually, there are questions. Can you see them?
I can't see them now, Cécile.
Okay. Maybe I can read it to you. I'll do my best. How would you
please.
Would you differentiate BA from ABC?
That's a very, very good question. That's a very good question. Both of these algorithms were developed in 2005. And for those of you who do not know, the originator of ABC, Professor Karabua, was a member of our team. I have to say that he developed the Bayes algorithm totally independently. The ABC algorithm totally independently from the Bayes algorithm. So he had finished his PhD at our lab long before he invented ABC, and long before we invented the Bayes algorithm. So by chance, they seem to be quite similar, but actually they are different. If you read the ABC papers, and if you read the Bayes algorithm papers, you will see the difference between them. The details are perhaps too tedious for me to explain, but if you read those two papers, you'll see that they are different.
Okay, there's another question. Has it been compared with other algorithms?
Sorry, I could not hear.
Okay, has it been compared with other algorithms?
Of course, it has been compared with many algorithms. And again, if you have a look at papers on the Bayes algorithm, you will see all of them have comparisons against GA, against ABC, sometimes against other algorithms too. ACO, PSO, all kinds of algorithms. I cannot say that in all cases we perform better. And this is governed by the no free lunch theorem. You know, no algorithm is perfect for all applications. So in some applications, the Bayes algorithm will be the best. In other algorithms, in other problems, the Bayes algorithm might not perform so well. So if you have a box of tools, it's better than you can use the right tool for the right problem.
There's another question. Could you please provide some suggestion on how we could improve the algorithm? Specifically, I am wondering if we could collect more data, improve the quality of data, fine-tune the model, use an ensemble of models, or regularly monitor and update the algorithm to enhance its accuracy.
Yes, certainly. You have suggested the solution yourself. So you have more data for training. You have all the suggestions you've made. They are good suggestions. So please follow them. And if you would like to contact us for more discussions, we are available. Our team is always ready to discuss with colleagues about how to use the Bayes algorithm. By the way, I've not mentioned that the Bayes algorithm, the code for it is available online, and people are welcome to download it. Asrul has produced a lot of code, and other colleagues as well. In MATLAB language. So yeah, we have all kinds of code for you to use.
We have many more questions. Tell me when I should continue. There's another one. Can the Bayes algorithm be used to select or reduce feature dimensions? If yes, how? How is the performance?
This has been done. It was done, I think, by our colleague, Dr. Pakyanatha. And I don't remember the details. If you formulate the problem as an optimization problem, if you want to find the optimum number of features, then you need to have an objective function to measure the performance, and then you feed that to the Bayes algorithm, and it will maximize or minimize the objective function for you. And that way, at the end of the iteration of the experiment, then you will find the best combination of features. So I can't describe, in general. We need to look at a particular problem. And if you like, you can look up the work done by Michael, and you will find that selection of features was, I believe, investigated by Michael and his team.
have another question. Could you introduce how Bayes' algorithm work on combinatorial optimization problems?
Right. So it's the same idea as described before. It's only how you perform neighborhood search that might be different, because in the case of the combinatorial problem, neighborhoods are different from the neighborhoods in the case of continuous problems. So you need to represent the solution, and then you perform various local search methods. Let's say you might change one bit of the solution. You might change one bit, or you might perform a simple local operation to ensure. You need to define the neighborhood correctly for combinatorial problem, and it's a little bit less straightforward than in the case of a continuous optimization problem. So, to summarize, the only difference is in the definition of the neighborhood of the local search. So you need to have appropriate local search techniques in order to explore neighborhoods in the case of combinatorial problems.
I have another question. Somebody is saying, I have done many applications using both BA and AC and found ABC much outperforming.
That it could be so. I cannot say because I don't see the your particular problems. It could be that ABC was good for your problems, but we have also tried ABC and the Bayes algorithm, and we have found that for our problems, for some of our problems, the Bayes algorithm performed better. So, they come from the same family. They use foraging, and the key difference in the ABC is some of the operators. That's all.
How do you choose the values of scout bees, elite bees, and best bees for different optimization problems?
Right. So I would say that that is something that you have to do by trial and error. That is why some people find it a little bit hard when they see 6 or 7 parameters and they don't know what to choose. We recommend starting with a set of numbers and then modifying the numbers until you get good solutions that suit you. But if you are really worried about having to select all these parameters, then try the 2-parameter Bayes algorithm. So then you only need to select 2 parameters: the number of elite bees, the number of scout bees, and the number of forager bees allocated to the elite bee. That's all. Yeah. So they are very, very simple.
How to choose the parameters in bee algorithms? Is there any literature available on this?
There is a theoretical study by Luca Baronti. He was in our team as well. He worked with our colleague, Dr. Castellani, and he completed his PhD a few years ago. And he did a study of the Bayes algorithm, theoretical study, and he looked into parameters. So you might want to look at his thesis. Luca Baronti.
Oh, okay, thank you. Could you tell us what inspired you creating this Bayes algorithm?
Right. Yes. It is interesting. I started being interested in optimization when I read about the genetic algorithm. And then later on, we read about the ant algorithm. So it was in the 90s. I read about the ant algorithm. And then I said, ants, they were social insects. They were well organized. How about another kind of social insect? So bees came to mind. And then I gave that to one of my master's students, and he started working on it. Then we recruited more bees. I mean, more people interested. And then, it all started. As I said, we were inspired really by the genetic algorithm and the ant colony algorithm. And by the way, Dervish Karabua did his PhD on the genetic algorithm. So he was our first PhD student working on on optimization, on intelligent optimization. So he finished his PhD in the mid-90s, and he went back to Turkey, and we kept in touch. We published a book together. And then I had not heard from Dervish for some years. And one year, he tried to contact me, and he said he had a nice algorithm. He did not tell me what it was. He wanted to help to get it adopted by MATLAB, he mentioned. And I said to him, no, publish it. Don't try to sell it, because, publish it. Then I never heard from Dervish again for some years. And then we worked on the bees algorithm. And later on, we found in 2005, when we published our first report on the bees algorithm, that Dervish also published something in 2005. So we never discussed the bees algorithm or ABC together at all. But by chance, we came to the same or very similar algorithms.
Okay, thank you.
Cecile, I realize that time is almost up. So if you have to go, then
many questions. So maybe we won't answer all of them. We are sorry for that.
Thank you very much, Cecile, for your help today. And thank you to everybody who attended and asked some very interesting questions. And I hope that you have found something useful, a bit of history about the bees algorithm, and the link with Dervish Karabua, of whom I'm extremely proud, because he's now a big name in the field of optimization. And I hope that Dervish will come to our bees algorithm workshop to present either this year or next year. We are in touch. We're still in touch now. Thank you. Thank you very much.
Thank you very much, Professor Duc Pham, for your time. This concludes today's webinar. Just a reminder that after closing the webinar window, you'll be asked to take a short survey with a few questions. Your feedbacks and suggestions are very important for us to further improve it. Thank you very much for filling this IEEE IES webinar survey. Thank you for attending. Goodbye. Goodbye.
Bye. Thank you.